Hey, what's up, guys? This is Chung here. So this time LeetCode number 2014, longest subsequence repeated k times. Right. So this one I'm not going to vote it because this one is pretty. Uh, how can I put it? Pretty mm, interesting. I would say a problem, but not in a very good way. I mean, okay. Anyway, so we have a subsequence, right? We have a string here. And then we have integer k. So it means that we need to find the longest subsequence repeated k times in the string, right? So for example, right, we have this BBA, right? It's repeated 2 times in the string in here, okay? And if there are multiple like substrings, right, who will have the same length, right, we need to return the lexicographically largest one. Okay, if there's no such subsequence, return empty. Okay. So for example, we have this kind of let's LeetCode, right? So k is equal to 2, which means that we need to find the longest substring which we got repeated twice, right? So we have a so the answer is let because let are repeated twice because here we have a let here and there's a let here, let, right? Okay, and yeah, actually see there's another another uh like subsequent string subsequence also repeated twice, which is ete. But since let is the lexicographically larger than this one, that's why we return the let, right? So here we return b because apparently b is the only one, right? And here we have ab k is equal to 2, which means that there's no such subsequence. Okay, here we have BBB, right? BBB, and here we have k is equal to 3, right? That's why this one is the answer. Okay. Yeah, I believe because I think this one is the basically the largest, right? And here we have some constraints here. K is within the range of 2000, and n is this. N is like uh greater than 2, but smaller than k times 8. This one is pretty interesting, right? And S is consisting only of lowercase English letters, right? So this one, so what does this one tell us? I mean, um, so basically, let's say we have the longest substring is S, right? So the longest substring S will be equals to what? Because this one times K has to be uh some subsequence, right? For the sorry, not S. Let's say the longest subsequence is T, right? So basically T times K has to be has to be the subsequence of S, right? And the length of S is N, right? So which means that the length of T is what is basically smaller or equal than the length of S divided by K, right? Which in this case is what it is 8, right? Basically this is S, right? And this is S and this is K, right? So the length of S divided by K will be the length of the T, right? Which is 8. So which means that the longest subsequence we can get given this constraint is it's 7 actually, because uh n divided by K is smaller than 8, right? It's pretty obvious, right? Because since we need this T to be repeated K times, right? And since we already have these constraints, then it's telling us, okay, so the longest T will be smaller than 8, which is 7 in this case, right? So what can we get from this one? Since we know the longest possible subsequence, we can get 7, which means that we can somehow use a brute force way to solve it. right? So with 7, what can we get? So we can even solve it within the 7 factorial time complexity, right? So what is the 7 factorial? This one equals to the total subsequence, right? The total subsequence given like a length of n strings, right? So that's the time complexity to find all the possible 7 factorial subsequences, right? Anyway, so that's some of the observation we need to make, right? And then and then the and in order to to find out, right, if a subsequence is repeated k times, right, then we need to do we need to do a simple helper function check, right, to check if a if a string t is a subsequence of s, right? So where should we start? I mean, so the way I just did it in a way that it works in a way, because I think, okay, so this another observation is that in order, so first we need to find basically the potential letters we can use. So apparently not all the letters can be used as part of the subsequence, even though we have only 26 English letters, right? But it's always good to only find uh, the possible valid letters that we can use, instead of always looping through all 26 letters, right? And so what are the letters that can be part of our final answer? Are apparently are the letters that appears more than k times, right? So let's say if the L, since we have k, right, k is equal to 2, let's say the count of L is 1, equals to 1, then obviously we cannot, so the L will not be part of our final answer, right? So when L is equal to 2, then we know, okay, we can use 1L, right? And then when the L is equal to 3, right, what does it mean? Means still 1L, right? 0. When L is equal to 4, okay, it means that we can use at most 2Ls, right? Because we need those strings to be repeated k times, okay? So that's some optimization we can use. And with those, actually the main idea for this one is just brutal force search, basically, and we just just search from the smallest, and then we gradually add some valid candidates to the current string, right? And since we are since we are getting we're trying to get the greatest, right? So the lexicographically largest letter strings with the same length, what we can do is that once we have the available candidates letters, when we add that letters one by one, we can add it from the greatest, from the biggest to the smallest, right? So that we can make sure so the first one is always the greatest, right? So what I'm trying to say is like this. Basically, let's say we have a T. So the letters. Let's say we have T, P, C, and A, something like this. Let's say we have the four letters that we can use, right? Let's say for T we can, after calculation, we can use 3 T's, 2 P, 1 C, and 1 A, something like that, right? Then what does it mean? It means that we're gonna try all the possible combinations or all the possible ways that we can concatenate by using this kind of 4 letters with this kind of count. So what can we do, right? Basically, we can just start from, let's say, so we can start from the length equals to 1, right? And then we gradually add those strings, right, into our candidates. So when the length is equal to 1, we have T, P, C, and A, right? So apparently the T, P, C, A are apparently the valid candidates, right? And if the current one is a valid candidate, we can try to add more on top of them, right? So for example, we have T here, right? So now based on this T here, we basically will try to loop through this candidates again. Of course, we can also maintain like a counters along with the candidates to make sure we still have some available strings to add to the to the current candidates. For example, this is the current candidates, right? I mean, for this one, we'll try to add TPCA respectively, right? So for T, we have T and T, right? We still can add it because we allow 3 T's in total, right? So here we have T and P, right? And then we have T and C, and then T and A, right? So for P, we're also gonna add the PT, right? And then PP, PC, and PA, right? For C, we do the same thing, okay? So basically, this is the way we are like generating all the possible subsequences, right? Basically, all the possible possible strings, right? Given this many of T, this many P, this many C, and this many A letters, right? So we add them, we could generate them from the length layer by layer. And then apparently, once we have the current candidates, right, we still need to check with the current. Let's say for the T and P, right? For T and P, is the current one times K part of the subsequence of S, right? Because here we're only generating the subsequence, but we need to multiply it by K, right? So this is like another thing we need to know that based on the answers here, right? Let's say the TP, right? So we have T and P. Let's say the K is equal to 3, right? So it means that how can we know if this TP are repeated K times in the S, right? So what we can do is we can just multiply this TP by 3, which is TP, TP, and TP, right? And then we just need to check if this one is a subsequence of S, right? So if this one is subsequence of S, then we know, okay, so this TP is repeated at least 3 times, K times, right? In this S. Yeah, because the TP may repeat it 4 times, but it's fine, right? As long as it's repeated at least 3 times, then we're good, right? Yeah, I guess so. No, this one is more like, I think it's like Bradford's BFS search, right? Basically, we search all the possible strings, right? All the possible like combinations, right? Combinations or permutations of this available letters one by one. So we search it basically from the bottom up. So the reason being is that we search it from bottom up this is because if we search it from top down. So when I say top down, I mean we search from 7 letters to 1 letters. Okay, but now as you guys can see, we're searching from 1 letters gradually up to 7. So the reason being is because I think most of the the subsequences are invalid subsequences. That's why if we search top down, we'll be wasting a lot of time trying to process the invalid subsequence. But if we search it from bottom up, which means we are starting from the valid ones, and then we're only processing those valid subsequences, that will be faster. We do a bottom up. Okay, so I think that's pretty much it. Let's start coding. I think my code might not be very the most concise one, but I think it's the one I wrote that makes sense for me. Let's see. Let's start with the helper function, right? Subsequence. So this one can tell us if the t is a subsequence of s, right? So I think everyone should know how to implement this, right? So we have 2 pointers, okay, length of t, right? So we have while I smaller than m and j smaller than n, right? So if the si is equal to tj, okay, then we move the j forward by 1, right? And then we always move I by 1, right? In the end, we return j is equal to n, right? We can do a small uh, mm, early termination, like if the j is equal to n, right? We return well, actually, we don't have to return here because if the j is equal to n, the while loop will be stopped automatically, right? Okay, so that's how we check if the t is a subsequence of s, right? Pretty straightforward. And then for the main code, we have this one s. So first, let's do a count, right? So we'll count a counter of s, right? And then so we have a count here, and I need since I'm also going to need to know like what are the allowed uh, count for each letters. I'll just do this allowed count. How about this one? Allowed count. Default dictionary int. How about this one? So for seeing count in count.items, right? If the count is it's either equal greater than k, right? And then we know, okay, so this count are the letters. Allowed count will be the c equals to the count divided by k. Like I said, so basically the allowed count stores all the letters, the valid letters along with its allowed count for it, right? So now we have that, and let's see what else. Let me see. So I mean here, I guess like I said, we can sort the letters, the available letters, from the biggest to the smallest, or we don't have to sort it. We can just blind. We don't care about the order while generating the next candidate. We just simply just sort the candidates array in the end. I think that should also work. So that I think will make this implementation a bit easier. So what I mean is like this, right? So for candidates, right? So for candidates, we start from this one. But like I said, since I'm trying to eliminate do some pruning by checking if we can add these current letters into the candidates. For that, I need to maintain like a counter along with the string, along with the candidate string itself. Otherwise, I have to do a counter each time to check the string. That'll be another O of n time complexity, right? Basically, I'm sacrificing a little bit space to get a better time performance, right? So for C in like letters, I think I can do this. Count. Okay, for C in count in allowed count dot items, right? I do something like this. So we have a count equals to be the default dictionary of int, right? And the count of C equals to 1, and then I do candidate of the append of so C of it count it along with it, right? So basically, so for each of the candidates, starting from the candidates, we start from the C, right? Each C and the counter for it is this, right? And then I have a while loop here, while loop true here, okay? And then for each of the time, since we're processing it layer by layer, basically every time, every while loop, we're gonna process the length plus 1 layer of candidates, okay? So if a new candidates gonna equals to this. So for the current string and the count in the candidates, right? We'll try to add the C, the letters or the characters from this allowed count one by one. Okay, so basically for C and the allowed, okay, allowed count. Okay, okay, in this allowed count dot items, right? So what do we check? We check this. So if the current count C, basically because the C is the one we're trying to add to the current candidate, right? If this one is smaller than the allowed count, right? Then it means okay, we can add this letter to it, right? So and then since we have a for loop here, right, we cannot reuse the count for all the for loop here. So which means we need to do a copy here. We have a new count equals to count dot copy. Right, we do a deep copy, and then basically, so for the new count, C will be increased by 1. Okay, and then we just do a new candidates dot append. Okay, we have current plus C. Oh, and this let me finish this one. I forgot to check the subsequent thing. So basically, if this one is allowed, and then the next thing we need to check is that if this new candidate is a subsequence of S, right? We do a is subsequence of S. So remember, the candidate is final answer, and this final answer needs to be repeated k times. That's why we need to check this. Okay, current dot C, right, times k, right? So if everything works fine, then this one is a new candidate, right? And then when do we break? So if not new candidates, so basically if there's no longer candidates, find we break, right? And then here we do a candidate equals to new candidate, right? And then here in the end we do basically we'll need to do a sort, right? So we do a sorry, that's my Siri. Candidate dot sort reverse equals to true, right? And then because the so remember the candidate has two items. The first one is the string itself. Second one is a dictionary. But in our case, all we care is the string itself. That's why we'll be sorting the only by the first element, which is the string, right? Because once the while loop is finished, so everything that's ended up in the candidates are all the strings, right? Who has the longest subsequence. So that's why we sort it, and so that we can get the lexicographically largest one, right? Okay, I think then we just need to return the candidates dot 0, right? Which is the biggest one, right? And then the 0, right? Because we need the 0 one. We need the first one, which is the letter, the string, right? if candidates, else empty, right? Because here the candidates can be empty, right? Because here we may not have any letters that's have any it's allowed, right? Yeah, I think that's it. So let's try to run it. Hopefully there's no error. Okay. Seems okay. Let's submit. Okay, cool. So it works, right? Yeah, I mean, so we have a sort here, right? As you guys can see, we sort this one in the end, or we don't have to sort it in the end because this one is pretty heavy in my opinion. Because let's say we have a very long like subsequent like 7 subsequences, and in order to sort it, we have to compare the strings one by one, right? And then we have to compare the strings to each of other strings, right? So what we can do is that when we try to process the letters, right? Because here, so here it's not the key is not guaranteed, right? So what we can do is that we can do it like this. We can have like sorted letters, right? And then equals to sorted letter allowed count dot keys, right? And then reverse equals to true, right? So if we sorted the letters, the available allowed letters at the very beginning, right? And then every time when we try to add this the new letters, if we do this, I guess, right, something like this. So if we do this, so now we don't have a allowed count, so we have to define another variables. So going to be allowed count, right? Dot c, right? Okay, cool. So right, so it's here, and then here we don't have to sort it because since we're always processing the biggest letter first, and then we're guaranteed that the first one in the candidate will be the biggest one, right? And then I think this should also work, and it should run faster. Oops. Oh, did I? Sorted letters. Oh, let me check. Oh, I think what I need to change here, right? So we change it here, but when we initiate the candidates here, right? We also need to make sure the initial orders in these candidates are also sorted from the biggest to the smallest, which means here we have to do this, right? But we don't have the count. Yeah, okay, so interesting. Allowed count. Actually, yeah, I don't actually, so for this one, we don't need this, right? We don't need this count here because all we need is C here, right? For the previous implementation, right? If we use this one, okay, and then yeah, and then obviously we don't need this one. We don't have that because it's a list, right? So yeah, so I think this should work. Let's try to run it again. Yeah, as you guys can see, this one is like a bit faster than the previous one because we remove that sort in the end, right? Yeah, but I think it's overall it's pretty much the same time complexity compared to the previous implementation, just a little bit of improvement to remove the sorting. Okay, right. Yeah, I mean, I think that's it, right? As you guys can see, actually, this one, it's, I would say just like a BFI search with a little bit of pruning, right? So the reason we do a BFI search, basically, so what actually we're doing here is that given all the available letters, right? We're trying to generate all the possible basically the combinations for those letters here, right? Layer by layer, right? Basically, that's the way. So this is this part is the logic to generate all the possible subsequences, right? Given this many letters, and for each of the for each of the string here, right? We check if that string times k will be is part of the S, right? So this one is pretty brutal force right here, and then we for each one we check this is subsequence. Yeah, and then we are. Yeah, I think that's it. I don't know what else I want to talk about for this one, and for time complexity, I honestly not quite sure about time complexity for this one. This one seems pretty complex or complicated, right? So because we have this is subsequence here, and then we have this while loop here, right? I mean, based on this kind of here, based on the number of the allowed letters, we have some different possible subsequence that we need to process layer by layer, right? And then, yeah, honestly, I'm not sure. Yeah, maybe that's a question you guys can help me solve, right? Yeah, I think that's everything I want to talk about for this one. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.